Come on, come on, come on, come on, come on, come on. There we go. Perfect. All right. Good morning, A1 Algebra 2 CP. This is May 12th. This is Tuesday morning. Happy Tuesday. Hopefully you're having a great morning, and I hope it's going to get even better now that we're going to talk about solving rational equations today. When we're talking about solving rational equations, all of the background information that we discussed in the past two classes, that being simplifying rational expressions with multiplying and dividing and adding subtracting, is all going to come back and is going to be relevant, so that's really important to consider. The other couple things I want to remind you of are just the usual stuff. Make sure you fill out the attendance form. Make sure that your mics are muted and your webcams are disabled. Unless you have a question, then please feel free to unmute your mic and speak up, or just type it in the chat if you don't feel comfortable. Either way, whatever works for you. I did post some practice problems on Google Classroom already on solving rational equations. I do expect that those are completed by the start of Thursday's class. The answer key is provided as well. If you have any questions, in addition to checking the answer key, like if you check the answer key and you still have questions, please feel free to reach out to me, no problem. I'll be happy to help you out. But in any case, we will have a graded progress assessment at the end of the week. This week we're going back to it. You got a little week off last week because there wasn't really enough information to assess, in my opinion. But now heading into rational equations, there's going to be plenty of time to do some assessments on those. And then we'll probably cap off with an assessment on word problems. And, you know, that may be just about it for our time together in Algebra 2 CP. So let's make sure we make the full use of our time. Let's make sure we do not waste any more time or do not use any more of our time unwisely. Let's get into some rational equations. So, given everything we've learned previously, we're now going to jump into solving rational equations. We're pretty much going to apply those skills to now just solve for x and check out stuff like that, all right? Before we do, however, consider a rational equation like this, okay? Consider a rational equation like this, and we're going to get back to this specific example in just a little bit. X plus 2 divided by x times x plus 4 is equal to 1 over x plus 4 plus 1 over x. Okay, consider something like that. It's just a random rational equation. It's one that we're going to try to solve and find a value for x that makes all that work out. Just looking at it off the top of my head, I have no idea what value for x makes that equation true, right? Like if I asked you just without doing any steps, I said, what value of x works for that equation? You'd be like, I don't know. But I certainly do know which values of x cannot work in that equation. So I don't know what x could equal without doing a lot of algebraic steps, but I certainly know what x could not equal. And in this particular case, notice that x could not equal anything that would cause the denominator to be 0. Because dividing by 0 is super bad news. That's like cardinal rule of math number 1. You cannot divide by 0. So any value for x that results in dividing by 0 is bad. It's impossible to actually get that. So right off the bat with a problem like this, I could say that x is not equal to negative 4. It could not possibly be negative 4, because if it were, and I plugged in negative 4 for x, then negative 4 plus 4 would be 0, and you'd be stuck trying to divide by 0, which we all know is bad news, right? Very similar to the idea of a vertical asymptote, where I look and say what value for x would cause a problem in the denominator. That's pretty much what I'm doing right now. There's another value, too, that would also cause a problem in the denominator, and that's 0 itself. If you notice, if I plug in 0 for x, then we'd have 1 over 0, and that's really bad as well. So in this problem, before I even tried to solve it or even showed you anything related to solving it in the slightest, we can definitely determine what x could not equal, and x cannot equal negative 4 or 0. These values in this particular case are what are known as domain restrictions. Okay? And domain restrictions are values for x, in this case, that result in dividing by 0. Okay? you may recall all the way back to the beginning of the year, or you may not recall, you may remember it now that I say it, all the way back to the beginning of the year when we started talking about domain and range for the very first time. It seems like ages ago now, but it was at the beginning of the year in September. We started talking about domain and range for the first time, and you had a problem kind of like this. It was like 1 over x minus 2, and it asked you for the domain of that function. That was on our very first summative assessment, a problem very similar to that, where it asked you for the domain of that function, and you had to say that x could be any value except for 2, because 2 minus 2 would result in dividing by 0. So the same idea applies here. You could have written that x could not equal 2, or you could have written it's negative infinity to 2, union 2 to infinity. Either way, both of those refer to the same thing. But it's really the same idea now transitioning into the fourth quarter. That's why we did it all the way back at the beginning of the year, because it was a good introduction to this concept of being unable to divide by 0. All right? The reason why we want to specify those domain restrictions is because just like with our square root equations, it is possible that we could get extraneous solutions. Oh yeah, they're coming back, extraneous solutions. Remember, extraneous solutions is kind of like a value that comes up through perfectly legitimate algebra, but when you go back to substitute it into your problem, it just doesn't work. And that can result for a number of reasons. When we dealt with square root problems, it most likely came from having to square root a negative number, and that being a very problematic thing. In this particular case, extraneous solutions come about from trying to divide by 0. Now, you may think, does that mean that when we solve these problems, we have to go back and check our answer for extraneous solutions? Like, do we have to say, okay, let's take our value, plug it in, and check to make sure it works? You certainly could, but a much easier way of doing that is just seeing, does it match our domain restrictions? These tell you what the extraneous solutions would be if they were to come up. So if I solve this problem and I get a solution of x equals negative 4 or x equals 0, I could just take 2 seconds, look up at my domain restrictions and say, oh, we can't have that, it's extraneous. So there's no need to plug all the way back in and check like we had to do with radical equations when we did square roots. You certainly could do that. I don't want to discourage that if you want to go ahead and try that and just plug it in and see if it works. It should if you found that it was a valid solution. But when we identify our domain restrictions, all you have to do is just take a look at those. All right, so that's all I really want to say on that front. When we solve rational equations, there's really just a couple steps that we are going to take in order to really tackle any one of these problems. All right, the first of which is we're going to try, as best we can anyway, we are going to try to factor and simplify the denominator. Okay, factor and simplify the denominators. We saw last class that when we tried to find the least common denominator, it was very difficult to do that if my expression was still unfactored. But once we broke it down and factored it, it was very easy to identify, oh, we need this piece, we need this piece, we need this piece. Without doing that, that's a very difficult thing to do. The next thing that we have to do after we factor and simplify the denominators is we are going to identify the domain restrictions. The reason why we take, again, just a couple seconds to do that is so that if we have to check for extraneous solutions, it's a quick glance. It's not a big, long plug-in process. If you didn't identify your domain restrictions, then yes, you would have to go back, plug into the function, see if it works, and that's a long process to do. When we identify our domain restrictions, it just tells us, hey, those values, if they show up, that's a sign of an extraneous solution. Next thing we have to do is we have to find the LCD. Find the least common denominator we then have to, number 4, convert all terms to have the least common denominator. It's like you want to have all your terms match that least common denominator. Remember, least common denominator is often abbreviated as LCD. We talked all about the least common denominator last class. And then lastly, number 5 is once they're all converted to the same least common denominator, we can really just shift our attention to the numerator and solve the numerators, which often results in an expression like either an Algebra 1 expression or maybe something that requires some factoring like we did in like October, November-ish. All right? So let's, oh, and of course, that involves checking for extraneous solutions at the very end. Okay, but again, that's just a quick glance. So let's take a look at an actual example in action here, and then hopefully you'll be able to get it handle for how these are done. I have 5 examples prepared for you today. I hope we can get through all 5. This is one of them, but we'll get back to that one a little bit. Let's do a little easier one first. We'll start with 9 over 28 plus 3 over x plus 2 is equal to 3 over 4. Okay? First thing I want to do is factor and simplify. Is there any factoring to do in the denominator? Not really. Everything's already broken down, so we're all set there. Next thing, identify domain restrictions. We identify here that what value for x could not work. I don't know which one could, but I certainly know which one could not. We'd say that x cannot possibly equal negative 2. Because if it were equal to negative 2, then negative 2 plus 2 would be 0, and I'd be trying to divide by 0, which we can't do. Okay? So very quickly I can say that x cannot equal negative 2. That's automatic. We just say that right away. Well, now I can go ahead and find my least common denominator. Notice that I have a factor of 28, a factor of x plus 2, and a factor of 4. So let's deal with the constants first, the 28 and the 4. What's the lowest number that both of those can fit into? Think of like that children's toy cube. You know what I was talking about last class, right? With the cube, they have to fit all the pegs into. Same idea. 28 is the least common denominator between those two things because 28 times 1 is 28 and 4 times 7 is 28. And then I also need this factor of x plus 2 in my least common denominator. If I don't, then this one will be happy and this one will be happy, but this guy will be like, hey, wait a minute, what about me? You're leaving me out of the party here. We need 28 and 4 fits into 28, so that's happy, and the x plus 2 is satisfied now. Okay? Now what I want to do, now that I've found that least common denominator, I want to convert everything to be out of that. So I'd like all of my denominators to look like that. And we have to kind of ask ourselves, what do I need to multiply each of those terms by in order to make this look like this, in order to make this look like this, in order to make this look like this? What do I have to multiply this by? Well, the first term here I have to multiply by x plus 2, right? The 28's already there. I need to multiply by x plus 2 in the numerator. So that's exactly what I'm going to do. Take the numerator that's already there, multiply by x plus 2. What do I need to do to get this term to look like this? I need to multiply by 28 because the x plus 2 is already there. We need 3 that's already in the numerator times 28. What do I need to do to make this look like this? Well, to get from 4 to 28, I need to multiply by 7. So I'm going to take the 3 that's already there and multiply by 7. I also need to multiply by the x plus 2 as well. Does everybody see why that's the case? And does anybody have a question? Please speak now or forever hold your peace, or maybe not forever. But hey, if you have a question, now's the time. Question about that? All right, all quiet over there. All right, so now that all your denominators are matched up, by the way, notice we can pretty much just ignore them. It's like if you're saying that, like, picture if you had a problem like this, 1/2 equals x over 2. Well, why even pay any attention to these denominators? Those denominators are already the same. We can just focus on the numerators and say, well, if 1 out of 2 equals some unknown thing out of 2, well, then that unknown thing has to equal 1, right? The same idea applies here. All of your denominators are now the same, so we could pretty much just ignore them. We don't need to pay attention to them anymore. Now we can go ahead and just focus on the numerators and say, well, 9 times x plus 2, which, by the way, that would be 9x plus 18, distributing the 9, plus 3 times 28. 3 times 28, I should be able to do in my head, but for whatever reason, I cannot do in my head right now, is 84. should be equal to 3 times 7, which is 21. 21 times x is 21x. And 21 times 2 is 42. Okay. Notice once the denominators match up, we don't have to really account for those anymore. It's the same argument as over here. Once your denominators are the same, we only have to pay attention to the numerators. So at this step here, we can focus only on the numerators once the denominators match. Okay. Now that I am able to just focus on the numerators, notice that this really just broke down to an Algebra 1 style problem where I have variables and constants. I'd like to get all my variables on one side. I'll probably choose to subtract the 9x over to here, and I'll get my constants all on this side. So let's combine like terms first. I get 9x plus 18 plus 84. That's going to be what, 102, I believe, is equal to 21x plus 42. Let's subtract the 9x from both sides. Let's subtract the 42 from both sides. And it looks like I'm going to get, what, 60 is equal to 12x. That's 21 minus 9. Divide both sides by 12. You get x equals 5. Okay. Now, how do you know that x equals 5 is not an extraneous solution? Well, it takes 2 seconds. Does it match our restriction of -2? Nope. So we know x equals 5 is a valid solution. You could certainly plug in 5 and see if this all works out, but that's not necessary. Any question about how that was done? Like I said, we're going to go through a couple more. I may ask you to stay just a couple minutes after. It shouldn't be too long though. Okay, here we go. Let's fly through some more. Ready? It won't take as long as that one, I promise. How about this? We got 1 over 3x equals 1 over 6x minus 6 over x squared. Okay? So here's our second problem. 1 over 3x equals 1 over 6x minus 6 over x squared. First thing, factoring. Is there any factoring to do in the denominator? Not really. Everything's already broken down enough. We can now identify our domain restriction. The domain restriction here would be 0 itself, because 0 times 3 would make 0, 0 times 6 would make 0, and 0 squared would make 0. That would be bad across the board. Our least common denominator now, look at the least common denominator first of our constants. 3 and 6 both fit into 6, because 3 times 2 is 6 and 6 times 1 is 6. We have x, x, and x squared, so at minimum I need x squared to accommodate everything. Notice if I just put 6x, this guy would be happy, this guy would be happy, but this one would be like, wait a minute, I'm x squared over here. Well, you'll leave me out over here. What's the deal? So, in any case, we want to make everybody happy. We don't want to make anybody mad. And we don't want anybody to start talking with a terrible gangster accent. So, what do I need to multiply 3x by in order to get 6x squared? Because now I'd like to convert all my fractions. That's 3x times, what, 2x would make 6x squared. So I need to take the numerator of 1 that's already there and multiply by 2x. Of course, you don't have to write 1 times 2x, just showing you that for the sake of, consistency. If there were 2 there, then it would be 4x. What do I need to multiply 6x by in order to get 6x squared? That's x. So I'm going to do the same to the top. The 1 that's already there times x. What do I need to multiply x squared by to get 6x squared? We're missing the 6. So I'm going to take the 6 that's already in the numerator and multiply by an additional 6. Now we can go ahead and combine like terms and simplify. All the denominators are the same, so we can disregard those. We could just pay attention to the top. We got 2x equals x minus 36. And this is now just Algebra 1 territory where we subtract x from both sides, and I get that x is negative 36. Okay. How do we know that that is not an extraneous solution? Well, we just take a quick look up here. Is that equal to 0? Nope. So we're good. Okay, we're good. Certainly, again, you could go back and plug in and solve. Make sense? Hopefully. A-okay? All right. Let's revisit the example we started with. I think we're ready for it now. Let's revisit the example we started with. X plus 2 over x times x plus 4 equals 1 over x plus 4 plus 1 over x. Let's revisit that example and now see if we can work with, a major league kind of problem here. First, we start with our domain restrictions. Everything's already factored. Notice that's a nice thing. We don't have to factor. So our domain restrictions here, we definitely cannot equal -4 because -4 plus 4 would be 0. We also can't equal 0 itself. That's what we already established over there. So those are our domain restrictions. Now our least common denominator. Here we have a factor of x, a factor of x plus 4, a factor of x plus 4, and a factor of x. I would need to have an x that makes this happy and this happy. And I need to have a factor of x plus 4 as well, because that now satisfies this guy and that one. Now I'd like to convert everything. And again, if you have a question, please ask. Don't feel like you're interrupting. I'd like to convert everything now to be out of that least common denominator. We have x times x plus 4 here. I would like to get x times x plus 4 here as well. And I'd like to get x times x plus 4 here as well. So what do I need to multiply this by in order to get this? Well, nothing. That is already the least common denominator, so we don't have to touch that at all. That's nice for us. Just leave the x plus 2 up top. What do I need to get multiply this by in order to get this? Well, I need the additional x on the outside, so I'm going to take the 1 that's in the numerator and multiply it by x. You get 1x. And what do I need to multiply this by in order to get this? That's your x plus 4. Does that make sense to everybody, hopefully? Now that all the denominators match up, again, we could pretty much ignore them and just focus on the numerators. I have x plus 2 should equal x plus 4. See that? We're just paying attention to the numerators now. Because the denominators are the same, we could just disregard them because those are already equal to each other. So now we just need to make sure the tops are equal to each other. This is, again, Algebra 1. Combine like terms. I get x plus 2 equals x plus x is 2x. Plus 4. Get all your constants on one side, get all your variables on the other side. I'll subtract x, subtract 4, and that gives me that x is equal to -2. How do we know, again, that that's a legitimate answer? I would look up here and I'd say, oh, it's not -4, and oh, it's not 0, so we're in the clear. We're in the clear. Any questions about that? All right, we got 6 minutes to go. 2 more examples. Let's do it. How about x divided by x plus 2 plus x, just regular old x by itself, equals 5x plus 8 over x plus 2. Kind of an interesting thing about this one is when we just have a variable or a constant by itself. You might be like, well, wait a minute, what's the denominator of this thing? Is the denominator x? Like, what's the deal here? But remember, if I just had, like, say, a plus 2, a plus x, a plus 5, a minus 7, anything just hanging by itself, remember, is a whole number. And any whole number can be expressed as over 1. Right? X may not be a whole number depending on what the value for x is, but anything can be treated like a whole number by putting it over 1. Does that make sense? So don't get tripped up by that. If you see just like a plus 5 just hanging out by itself with no denominator, it doesn't mean it has no denominator. It means that the secret hidden denominator is 1, because anything divided by 1 is just itself. It's like the same thing here. I'd say, what's the coefficient of that? You might be like, well, there is no coefficient, but it's really just 1. The same thing here. Okay, so just make sure you account for that. Please do not make the mistake of saying, oh, the x has to be accounted for in the LCD. That is not the case at all. There's no factoring to do after that, so now I can go ahead and find my domain restrictions. You can see that x cannot be equal to -2 in this particular case, because that would cause dividing by 0. Again, notice when we do our domain restrictions, another point is make sure you're only looking at the denominator. It doesn't matter, like we don't have to find out what value for x makes the numerator 0. The numerator being 0 is fine, because 0 divided by anything is 0. It's when you have 0 in the denominator that's the trouble. That's where the trouble happens. So we identify our domain restriction. Our least common denominator here is, hopefully everybody can just see that, it would be x plus 2. That would make this happy, and 1 times x plus 2 would, of course, be x plus 2, so that's easy too. I'd like to now convert everything to be x plus 2. You might notice there's not a lot to do here as far as the conversion step goes, because a couple of our fractions are already out of x plus 2. this one, so we just leave it alone. This one we need to multiply by x plus 2 on the numerator, so I'm going to do exactly that. And this one's already x plus 2, so we can just, again, leave that the same. Hopefully I'm not going too fast. Hopefully it's all matching up here. Now that all your denominators are equal, I can go ahead and just focus on the numerators. This is now going to be x plus, we're going to distribute here, x squared plus 2x is equal to 5x plus 8. Everybody see that? Again, we can do that. We're allowed, so to speak, to do that because the denominators already match. So we can just now shift our focus to the numerators. And now, hopefully this alarm is going off in your head. Your Algebra 2 instincts are in high gear right now because you're like, ooh, x squared just showed up in an equation. What do we have to do when x squared shows up in an equation? Factor, of course. So that should be an immediate indication when you see x squared that it's like, ooh, I need to factor. But, before I factor, what do we need to do before we can factor? Of course, set equal to 0. So I'm going to do exactly that. I'm going to move the 5x over to here. I'm going to move the 8 over to here by subtracting 5x and subtracting 8. And now let's see what we got. We have x squared. Here we have x plus 2x is 3x minus the 5x we brought over is minus 2x. And then minus 8 is equal to 0. This can break down now to be, let's see, we need x and x to make x squared. I need different signs to get my negative 8, and it looks like I'm going to need negative 4 and plus 2. And so that comes out to be one solution of x equals negative 2 and one solution of x equals 4. So this problem in particular has two solutions, which can happen in an equation, right? And we're all ready to go about our day, and we're happy with that. Right? Wrong. Wrong. Take a look. Ooh, x equals 4 is fine, but x equals negative 2, didn't we say that that was one of our restrictions? That was a domain restriction. We can't have this answer. This answer is extraneous because it would result in dividing by 0. And that's how fast it really takes to just check for extraneous solutions. And so you would say that this problem has only one solution. That one solution is of x equals 4. It also has one extraneous solution. That extraneous solution is x equals negative 2. Does that make sense to everybody? All right, I know it's 10:30. I have one more problem that I'd really like to show you today. If you have to leave, I totally understand. It is going to be recorded and uploaded, so you can watch it later. But I'd appreciate it if you could just stick around for a couple more minutes as I go through this final problem with you, just because it's important. But again, no judgment if you have to go. Let's take a look at this final problem here. We have 1 over x squared minus 8x plus 12 plus 1 over x minus 2 equals x minus 5 over x minus 6. I'll go through this one quickly. It looks like a pretty scary problem, but it's really not that bad. First thing to do is factor. Again, your Algebra 2 instinct should kick into high gear right here. You should say, ooh, x squared, and it's a trinomial. Definitely need to factor. That's going to factor down to, let's see, x and x. We need two of the same sign because we're multiplying to a positive. And I need a, minus 6 and minus 2, I believe. And that's plus 1 over x minus 2 equals x minus 5 over x minus 6. Okay? Now that I factored, I can go ahead and find my domain restrictions. X in this problem could not be equal to 2 because 2 minus 2 would be 0. And x in this problem could not be equal to 6 because 6 minus 6 would be 0. So both of those are problematic. That's why we identify that x could not equal those values. Now I go forth and find my least common denominator. My least common denominator in this problem would be x minus 6 times x minus 2. I need a factor of x minus 6 to make this happy and this happy. I need a factor of x minus 2 to make those two things happy. I'd now like everything to look like that least common denominator, x minus 6 times x minus 2 plus x minus 6 times x minus 2 equals x minus 6. That's a lot of writing. I know this step is a lot of writing. Times x minus 2. I'd like to convert everything, What do I need to multiply everything by in order to complete that conversion successfully? Well, this one I don't need to change it at all. That's already looking like that. This one I need to multiply by x minus 6. So that becomes 1 times x minus 6 in the numerator, which is just x minus 6. This one I need to multiply by x minus 2. So I'm going to take the x minus 5 that's already in the numerator and multiply by x minus 2. Do you see why? Because to get from here to here, this is the missing piece. So we need to apply that on the numerator as well. Now that all your denominators match up, we can just pay attention to the top. That gives me 1 plus x minus 6 is equal to, we're going to multiply these together to get x squared minus 2x minus 5x plus 10. Again, that alarm should be going off in your head when you see x squared. Prime time indicator that we need to factor. In order to factor, we need to set equal to 0. So let's do exactly that. I'm going to add, let's see, 1 minus 6 is negative 5. So I'm going to add 5 over to this side. And I'm going to subtract x over to this side. That gives us that 0 is equal to x squared, negative 2x minus 5x, negative 7x minus an additional x, so minus 8x. And then 10 plus 5 plus 15. We can break that down now by factoring. Again, we need x times x to make x squared. Same sign to make that positive value at the end, and they both have to be negative to come out to this negative 8. And the factors that are going to work here are 3 and 5. So therefore, that gives me 2 solutions to this problem. X equals 3, because 3 minus 3 would be 0, and x equals 5, because 5 minus 5 is 0. In this particular case, both of those solutions are valid because neither match the domain restriction. So we'd say this problem has 2 solutions, one of x equals 3 and one of x equals 5. Whew. Last chance, does anybody have any questions about that? Good question, Luke asked, is there a PA due? Not for next class, but there will be one assigned after class on Thursday. So there are practice problems that I've uploaded on Google Classroom with the answer key that I would like you to try for next class. It's only to your benefit to try them. But after next class, so after Thursday's class, that's when we're going to have a PA that's going to be assigned and due Sunday night, just like our routine was previously. I really appreciate everyone sticking around for a couple extra minutes. It means a lot. So hopefully you got a lot out of this. Hopefully you learned stuff. If you do have any other questions, please feel free to reach out. But again, have a fantastic day. Thank you again for being respectful. Remember to watch the video back if you need to. It is uploaded, so you can go ahead, or it will be. It's not yet. It's not currently uploaded. That would be pretty cool if we could do it in real time. But it will be soon, so please make sure you go back and watch if you need to. Have a fantastic day. I will see you Thursday. Bye, everyone.